Compare and contrast the plot of current magnitude as a function of frequency with these plots for two additional circuits, circuit X on the left and circuit Y on the right, plotted on the same scale as our original circuit in the center. Yes, the character of these additional plots may appear subtly altered, but if you think about it, they're all permutations of the same general purpose plot of current as a function of frequency. Circuit X's plot of current as a function of frequency appears to be squashed, spread out, and weakly defined. In contrast, circuit Y's plot of current as a function of frequency is clear, sharp, and distinguished. Our original circuit is kind of a mix of both plots. This being said, current for all three circuits still peaks at the resonant frequency. At the resonant frequency, we'd again expect voltage across the capacitor and inductor to be equal in magnitude, yet completely out of phase with one another. Really, the only thing left to discuss about series resonance is all the admittedly esoteric math associated with quantifying the shape of current as a function of frequency. Ideally, we should be able to come up with a handful of quantifiable properties that allow an individual to quickly ascertain if the circuit under inspection possesses a clear and distinguished response, as in circuit Y, or a muted and soft response, as in circuit X. Perhaps the most distinguishing differential between our three examples is behavior at or near resonant conditions. You note a pretty wide region of frequencies to the left and right of circuit X's resonant frequency yield almost indistinguishable results. A couple hertz to the left or right really wouldn't matter one way or the other, as source current inside this wider band doesn't change very much, as evidenced by the shallow slope. It could be said that circuit X operates at peak power conditions inside a very wide, extremely permissive band. This is in direct contrast to the behavior of circuit Y at or near resonant conditions. 1 or 2 hertz on either side might still yield desired results. However, any further departure from resonant frequency and one quickly falls off the edge of a very, very steep cliff. It could be said that circuit Y operates at peak power conditions only inside a very narrow, extremely selective band. The property I'm referring to is known as selectivity. The generally accepted standard for gauging selectivity of a circuit is the range of frequencies inside of which the circuit experiences half power or greater. For this reason, the left and right boundary frequencies of this region are often known as the lower and upper half power frequencies, F1 and F2. They are also known as the cutoff frequencies, the band frequencies, or corner frequencies, depending on which industry jargon you're employing. Operating the circuit at any frequency inside this band would experience half power or greater. Operating the circuit at any frequency outside this band experiences half power or less. This is perhaps the most practical application of resonant circuits, even more so than developing electroshock weapons. Consider several senders broadcasting information on several different frequencies. By tuning a receiver to a desired frequency, everything unwanted is rejected and only inside that small band of frequencies is admitted, or shall we say, selected. You'd think that there'd be a symmetry between the lower and upper half-power frequencies, F1 and F2, such that they're equidistant from the resonant frequency, but they are not, and only in special occasions can we assume this to be true. Two formulas can be used to solve for the lower and upper half-power frequencies, F1 and F2, the derivations of which I will not demonstrate because it is a mathematical goat show of epic proportions. I will, however, explain the general origin of these formulas. A condition of half power implies that source current is equal to the maximum current divided by square root 2, y 1 over square root 2. You recall that power, among its many means of computation, can be calculated at any point on the selectivity curve as source current squared times the impedance. Peak power at resonance occurs because peak current flows through the resistor. This would be calculated as peak current squared times resistance. This yields a known maximum power condition, P max. If current happens to be 1 over square root times peak, or roughly 0.707 current peak, the power calculation yields 1 over square root 2 peak current squared times the impedance. 1 over square root 2 squared is half peak power. Get it? Any frequency resulting in current above 0.707 or 70.7% of peak would yield half power or greater. And any frequency resulting in current below 0.707 or 70.7% of peak would yield half power or less. What are these half power cutoff frequencies? I will skip the derivation because I don't have all day, but the lower half power frequency F1 can be calculated using this weighty formula, and the upper half power frequency F2 can be calculated using this similarly weighty formula. Notice these two formulas are almost identical, and only a small, easily overlooked negative sign differentiates the two. Don't screw up the formula by overlooking the negative sign. For our original illustrated example, an application of the first half power formula suggests F1 equals 51.8 Hz. A subsequent application of the second half power formula suggests that F2 equals 84.9 Hz. Like I mentioned earlier, the half power region isn't exactly symmetric around the resonant frequency for this particular circuit, because the lower half power frequency is separated from a resonant frequency of 66.3 Hz only by 10.5 Hz, whereas the upper half power frequency is separated from a resonant frequency of 66.3 Hz by 18.6 Hz. Let's check our work. If everything I've been saying is true, at either one of these half power frequencies, source current should be our peak current times 1 over square root 2, or 0.707 times peak. Recall we observed a peak current of 1.2 amps. We should therefore expect a current draw of roughly 849 milliamperes at either one of these half power frequencies. For the lower half power frequency of 51.8 Hz, the complex impedance for the 12 microfarad capacitor will be 256 ohms at an angle of -90 degrees. The complex impedance of the 400 millihenry inductor will now be 156.2 ohms at an angle of positive 90 degrees. The total impedance will be the summation of ZR, ZC, and ZL. Substituting our given values yields a total impedance of 141.3 ohms at an angle of -45 degrees. Notice the negative angle indicates total impedance has a capacitive nature, as we might expect. Application of Ohm's law demonstrates source current at the lower half power frequency will be approximately 849 milliamperes at an angle of 45 degrees. This verifies our earlier expectations. Note current leads by 45 degrees for this capacitive arrangement at the lower half power frequency. Let's now examine voltage distribution within this series circuit at the lower half power frequency. An application of Ohm's law demonstrates voltage across the resistor will be 84.9 volts at an angle of 45 degrees. Another application of Ohm's law demonstrates voltage across the capacitor will be 217.5 volts at an angle of -45 degrees. And finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to 132.7 volts at an angle of 135 degrees. As previously, take a moment to weigh the consequences of operating at the lower half power frequency, i.e. lower than the resonant frequency. Capacitive impedance went up. Inductive impedance went down. Total impedance seems to favor a somewhat capacitive nature. Source current goes down and starts leading supply voltage as we'd expect for a capacitive circuit. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and inductor, and more was dropped across the capacitor. In summary, at an excitation frequency below the resonant frequency, this circuit appears more capacitive. Importantly, given this is the lower half power frequency, source current is roughly 849 milliamperes as predicted, being 1.2 amps, a maximum current, divided by square root 2. I leave as an exercise to the viewer to solve for these same electrical properties at the upper half power frequency of 84.9 Hz. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. At the upper half power frequency of 84.9 Hz, note source current will be roughly 84.9 milliamperes at an angle of -45 degrees, i.e. 1.2 amps, divided by square root 2. Notice the negative angle indicates source current now lags supply voltage for this largely inductive arrangement at the upper half power frequency. Again, take a moment to weigh the consequences of operating at the upper half power frequency, i.e. something higher than the resonant frequency. Capacitive impedance went down. Inductive impedance went up. Source current goes down and starts lagging supply voltage, as we'd expect for an inductive circuit. Finally, voltage distribution within the series circuit changed. Less voltage was dropped across the resistor and capacitor, and more was dropped across the inductor. In summary, at an excitation frequency above the resonant frequency, this circuit appears more inductive. Importantly, given this is the upper half power frequency, source current is roughly 849 milliamperes, as predicted, being 1.2 amps, i.e. maximum current, divided by square root 2. Moving on. Let's now discuss bandwidth and quality factor. The half power or greater region between F1 and F2 is known as the bandwidth. For our particular circuit, it has a bandwidth of 84.9 Hz, minus 51.8 Hz, or 33.2 Hz. Another property associated with resonant circuits is something known as quality factor, sometimes abbreviated as QF. Explaining quality factor is like trying to nail jello to a tree, and it'll take some time and repeat exposure for you to truly understand its significance. On a basic fundamental level, quality factor compares the reactive power exchange between the reactive elements with that amount of real power dissipated by the circuit. In its purest form, quality factor is calculated as the ratio of reactive power placed in storage over the real power. However, it can be calculated using a far easier method. Recall that power, among its many means of computation, can be calculated as current squared times impedance. If we wish to calculate the reactive power exchange between the reactive inductor and the capacitor, the top half of our ratio, we would square source current and multiply it times one of the reactive impedances, that of the inductor or the capacitor. After all, they're equal at conditions of resonance. Similarly, to calculate the real power dissipated by the circuit, the bottom half of our ratio, we'd square source current and multiply it times resistance. Note the like I squared terms in the numerator and denominator. I squared cancels out. We're left with quality factor equals the ratio of the reactive impedance, inductor or capacitor, whichever one you want, over the resistance. For our initial example series circuit at conditions of resonance, the capacitor and inductor each have an impedance of 200 ohms, whereas the resistor has an impedance of 100 ohms. Substituting our given values yields a quality factor of 2. This is a pretty crappy quality factor, but it gets the job done. Like I said, understanding the significance of quality factor will take some exposure. However, it needs to be stated up front that quality factor is a super handy cheat code for other calculations. Recall that in order to calculate bandwidth, we first had to calculate the lower and upper half power frequencies using two super weighty formulas and then subtract them to find the difference. While this method does work, there's a much quicker method of doing so, where bandwidth is the resonant frequency divided by quality factor. Substituting our given values for our initial example series circuit directly yields a bandwidth of 33.2 Hz, exactly as we previously obtained without all the toil and tears. Additionally, quality factor can also be used to quickly approximate the voltage across the reactive components at conditions of resonance, where voltage across the reactive components at conditions of resonance is equal to the quality factor times the supply voltage. For our original series circuit, quality factor of 2 times the source voltage of 120 volts yields 240 volts as we previously attained, again without all the heartbreaking labor. Finally, when quality factor is determined to be 10 or greater, synonymous for a circuit with a super tight, very narrow bandwidth, it's relatively safe to assume that the lower and upper half power frequencies are indeed symmetric and equidistant from the resonant frequency. This obviously wasn't true for our initial example. However, consider a series circuit employing a 40 ohm resistor, a smaller capacitor with a capacitance value of 6 microfarads, and a larger inductor with a value of 960 millihenries. Let's make this an illustrated example. See if you can determine the resonant frequency of this circuit and determine the electrical properties of this circuit at conditions of resonance, specifically total impedance, source current, and voltage across the resistor, capacitor, and inductor. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. An application of the resonant frequency formula demonstrates this circuit also experiences resonance at roughly 66.3 Hz. It makes sense. We double the inductance and halve the capacitance. As a result, the resonant frequency stays put at 66.3 Hz. The 40 ohm resistor presents a complex impedance of 40 ohms at an angle of 0 degrees. At the resonant frequency of 66.3 Hz, the 6 microfarad capacitor presents an impedance of roughly 400 ohms at an angle of negative 90 degrees. At the resonant frequency of 66.3 Hz, the 960 millihenry inductor presents an impedance of roughly 400 ohms at an angle of positive 90 degrees. As we expected, the capacitive and inductive impedances at conditions of resonance are equal and opposite to one another. Total impedance is the sum of ZR plus ZC plus ZL. Substituting our given values yields a total impedance to be 40 ohms at an angle of 0 degrees. As we expected, the capacitive and inductive impedance contributions cancel each other out at conditions of resonance, such that the total impedance appears to be only the resistive component. This represents the lowest impedance magnitude, and as such, we'll expect source current to peak. An application of Ohm's law demonstrates source current will be 3 amps at an angle of 0 degrees. Source current is in phase with supply voltage. Given this is a series circuit with a single path for current, it can be said 3 amps at an angle of 0 degrees flows through all three elements forming the series connection. IR equals 3 amps at an angle of 0 degrees, as does IC and IL. Let's now examine voltage distribution within this series circuit. An application of Ohm's law demonstrates voltage across the resistor will be 120 volts at an angle of 0 degrees. Another application of Ohm's law demonstrates voltage across the capacitor will be equal to an astronomical 1.2 kilovolts at an angle of negative 90 degrees. Finally, yet another application of Ohm's law demonstrates voltage across the inductor will be equal to an astronomical 1.2 kilovolts at an angle of positive 90 degrees. This is obviously a comically exaggerated example, intended to dramatically illustrate characteristics of series resonant circuits with large quality factor values, notably extremely high voltages across the reactive components at conditions of resonance. Speaking of quality factor, what's the quality factor for this circuit? What are the corner or half power frequencies? And what's the bandwidth for this particular circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The short and sweet quality factor formula demonstrates the reactive components have an impedance 10 times that of the resistive component, therefore the quality factor for this circuit is 10. The bandwidth is the resonant frequency divided by quality factor. Substituting our given values, we find an extremely small bandwidth of only 6.6 Hz. The high quality factor is indicative of a far more selective circuit, thus a smaller bandwidth. Let's now determine the lower and upper half power frequencies. I suppose we could use the weighty half power frequency formulas. However, given the circuit has a quality factor of 10 or greater, we are allowed to assume the half power frequencies are perfectly symmetric about the resonant frequency. Given a 6.6 Hz bandwidth, 3.3 Hz to the left of the resonant frequency will be F1, and 3.3 Hz to the right of the resonant frequency will be F2. Substituting in our given values yields F1 to be roughly 63 Hz and F2 to be roughly 69.6 Hz. If you're hard-headed enough or had a lot of time on your hands, you could use the weighty half-power frequency formulas that are only slightly more accurate than obtained using this approximation allowed by a quality factor of 10 or greater, however at the cost of much, much more work. Note the resonant frequency of this circuit is the same as our original circuit. However, we observed a substantially different properties at resonance because this new circuit employed a smaller resistor, a smaller capacitor, and a larger inductor. For series resonant circuits, that's a surefire combination to increase the quality factor. At conditions of resonance, note the reactive components have much higher impedances than the resistor, and all elements experience a peak current of 3 amps. As a result, the reactive components at resonance experience extremely high voltage differentials, equal in magnitude, yet perfectly out of phase with one another. This is indicative of a substantial amount of reactive power being juggled back and forth between these two reactive elements. As we did with the original circuit, one could perform a frequency sweep analysis of this modified circuit, plotting source current magnitude as a function of frequency. Doing so, we observe the following behavior. It's perhaps worthwhile to compare this new modified circuit, incorporating a smaller resistor and a smaller capacitor and a larger inductor, with our original circuit. As did the original circuit, only at conditions of resonance, in this case 66.3 Hz, does current peak. Only this time it does so in a particularly dramatic fashion. Only inside a very, very narrow bandwidth, in this case 6.6 Hz wide, does our current ever reach roughly 0.707 or 70.7% of peak current. Only inside this highly selective region, between 63 Hz and 69.6 Hz, will the circuit experience half power or greater. Series resonant circuits with smaller resistors, larger inductors, and smaller capacitors have higher quality factor values, smaller bandwidths, and as a result are more selective. Conversely, series circuits with larger resistors, smaller inductors, and larger capacitors have lower quality factor values, larger bandwidths, and as a result are less selective. To reiterate this concept, consider these 3 plots of source current as a function of frequency for 3 different circuits. The one in the middle is our original series AC circuit, consisting of a 100 ohm resistor, a 12 microfarad capacitor, and a 480 millihenry inductor. At the resonant condition of 66.3 Hz, current peaks at 1.2 amps. As a quality factor of 2, an asymmetric bandwidth of 33.2 Hz between 51.8 Hz and 84.9 Hz. At resonance, we observe voltage across the reactive elements to be 2 times the source voltage. The plot on the right is a modified series AC circuit consisting of a smaller 40 ohm resistor, a smaller 6 microfarad capacitor, and a larger 960 millihenry inductor. At the resonant condition of 66.3 Hz, current peaks at a much larger 3 amps. It has a quality factor of 10, a bandwidth of 6.6 Hz, symmetrically distributed between 63 Hz and 66.9 Hz. At resonance, we observe voltage across the reactive elements to be 10 times the source voltage. The plot on the left is a modified series AC circuit consisting of a larger 200 ohm resistor, a larger 24 microfarad capacitor, and a smaller 240 millihenry inductor. This circuit is dirty, manky smelling, and appears to have a fine coating of moss growing on it. Given these component values, we'd also expect it to experience resonance at 66.3 Hz, albeit a resonance of significantly less pizzazz than the other two. Plotted on the same vertical scale as the other two, the plot of source current as a function of frequency looks as limp as an earthworm caught in a rain puddle, and it's hard to tell what source current is actually doing. Even if we zoom in, we find source current weakly peaks at a resonant frequency of 66.3 Hz, however at a much smaller value of 600 milliamperes. It has a quality factor of 0.5, meaning at conditions of resonance, the impedance of the reactive components are only half that of the resistor. In this case, half of 200 is 100 ohms. This implies the circuit has a wide bandwidth of 132.6 Hz, meaning it's super permissive, i.e. extremely non-selective. Given such a low quality factor, the bandwidth is obviously asymmetric, and we need to resort to some heavy lifting to determine the lower and upper half power frequencies. I'll save you the trouble and solve them myself. The lower half power frequency F1 is approximately 27.5 Hz, and the upper half power frequency is 160.1 Hz. Anything inside this wide, extremely non-selective range will experience half power or greater, and even that won't be as much compared to the other two circuits given such a small peak current. Finally, at resonance, we would expect voltage across the reactive elements to be half the source voltage, in this case 60 volts. Note for this lackluster circuit, the voltage across the reactive components isn't nearly as high as the other two, given its low quality factor value. In summary, component levels dictate not only the resonant frequency, but also the performance at conditions of resonance. I kind of illustrated everything at once. However, we can look how the resistance value and the ratio of the inductor and capacitor independently influence performance at resonance. Consider a series resonant circuit with a fixed inductor and capacitor. With a resistor of a given value, we might expect the plot of source current as a function of frequency to look like this, where current peaks at the resonant frequency and it has a given bandwidth. If we kept the inductor and capacitor the same but decreased the resistance, the resonant frequency will remain fixed. However, the smaller resistor would permit more current to flow. As such, we might expect the plot of source current as a function of frequency to look like this, where current peaks at a higher value. As a result, the circuit has a higher quality factor and a smaller bandwidth. Conversely, if we kept the inductor and capacitor the same but increased the resistance, the resonant frequency will remain fixed. However, the larger resistor would permit less current to flow. As such, we might expect the plot of source current as a function of frequency to look like this, where current peaks at a lower value. As a result, the circuit has a lower quality factor and a larger bandwidth. In summary, series circuits with lower resistances experience higher current at resonance and have higher quality factor and tighter bandwidths. Let's now keep resistance the same and consider how the ratio of the inductor and capacitor influences the performance at resonance. As we observe, circuits employing larger inductors and smaller capacitors exhibit higher quality factor values, and circuits employing smaller inductors and larger capacitors exhibit lower quality factor values. Consider a series resonant circuit with a fixed resistor and a given inductor capacitor value. We might expect the plot of source current as a function of frequency to look like this, where current again peaks at the resonant frequency and it has a given bandwidth. If we kept the resistor constant, but increased the value of the inductor and decreased the value of the capacitor by the same amount, i.e. we increase the inductance to capacitance ratio, the resonant frequency and peak current will remain fixed. However, the larger inductor to smaller capacitor ratio would tighten the bandwidth considerably. Conversely, if we kept the resistor constant but decreased the value of the inductor and increased the value of the capacitor by the same amount, the resonant frequency and peak current would remain fixed. However, the smaller to inductor to larger capacitor ratio would spread the bandwidth out quite a bit. Like I said, the significance of quality factor is a little difficult to conceptualize at first, but I'm hoping these graphs and the previous exercises illustrated how quality factor conveys a measurable indication of how selective a circuit is or is not, and how component level values not only specify when resonance occurs, but also the performance at conditions of resonance and at conditions of other than resonance. All right, that's about it for today. Yes, I have left a lot unsaid about resonance, but as I said in the beginning of this lecture, I categorically refuse to wrestle that dirty, dirty pig. This being said, with this lecture now in your pocket, you are probably well prepared to dive into the dirtiest pig pen of your choosing and give it a go if you feel so inclined. As for me, I am done with this pig, and I'll just sit back and watch you get muddy. Have fun. In conclusion, this lecture examined fundamental properties about series AC resonance. We learned series AC circuits experience resonance at frequencies when the capacitive and inductive impedance components cancel each other out. At conditions of resonance, impedance magnitude valleys, and source current peaks. Additionally, we examined the significance of the quality factor on the selectivity of a given circuit and examined the means of calculating bandwidth and half-power frequencies. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.